Hi, welcome to 16-Bit Bench. Matt here. Today we are revisiting the Game Gear Raspberry Pi project. This will be part 4 in I'm hoping 4-part series. So parts 1, 2 and 3 will be on cards, popping up now. So if you haven't seen those, please go back and look at those. There's a lot of information there and some, obviously how we got to this point. So in the first video we covered the kind of concept and the parts that you'd need. In the second video we covered wiring up the Teensy as a USB device and how to integrate the buttons for the Game Gear and 3D printing some enclosures for that. In the third video we talked about how to remove parts from the Raspberry Pi, so slim it down. We used a hot air rework gun to do that. And we wired up some extensions to some stuff inside the Pi as well, so like the USB, removed USB connectors, connected up extensions to those, hardwired a cable for the Teensy. Then we looked at the buttons and the touch sensors and that sort of stuff. In this video, hopefully the final video in the series, we will be looking at the power and soundboard integration into the Raspberry Pi. So the soundboard is going to be using the Game Gear native soundboard that comes with the Game Gear, and that's so we can retain use of the speaker and the volume control, and also the headphone jack will all work as they did with the original Game Gear. And the power board, the idea there is that we will have a power switch. Actually, this is upside down. There we are. Is that better? So we've got the power switch on the top there. Turning on the unit will supply power to the Raspberry Pi and everything will boot up as usual. And then the idea is turning off the unit will not immediately shut down the Pi, but will tell the Pi to enter shutdown mode. And after about 10 seconds or so, we have a circuit in there that cuts power to the whole thing. So the idea being that when people build these handhelds, they quite often treat them as solid state machines. That means they just cut the power to it. The problem with that is it's not a solid state machine. It has a flash memory, and flash memory is volatile memory over time. So it's, so you read and you write to it. If you cut the power to it mid-read, mid-sector read, it could corrupt it. So you'll probably shut it off 100 or 200 times. It's absolutely fine. But the 101st time you shut it off, the next time you turn it on, it won't boot because your card's corrupted. And that's because we didn't shut down the Pi first. So I wanted to avoid that in this build. I wanted to be a bit more smart about it, and that's what we're looking to achieve. So first of all, what we're going to do is look at the soundboard integration. Then we're going to look at a circuit diagram for the power circuit and how I expect that to work. Then we're going to build that. I'm going to show you that built, test it, and then we're going to put it inside the Pi and get it to work. So there's a lot of work to do in one video. Let's crack on. So I just wanted to cover the soundboard before we move on. It's really simple actually to integrate it. It has a 5-pin header down here. It's it's pretty gunky from where I've soldered to it, but basically it's 5 volts ground left and right. So that's all you need to solder to it. And then so I've got the left and right audio coming from the screen, the HDMI screen, over a disconnect, and then power and ground there. So yeah, you can see the Game Gear board's being recapped. I've used surface mount ceramics and some tantalum caps there rather than electrolytics, and that's just because I had those hanging around. On the Pi, I think I have the volume turned to 100%. But yeah, the whole board works, and it's really simple that way. So by doing this, the functionality I get is I get the headphone jack working. So if you plug headphones in, it disconnects the external speaker. Obviously, the external speaker works fine as well, which I think is actually doing like a left-right down mix, which is interesting because it's only one mono speaker, but the Game Gear's stereo. So that's how we've integrated the soundboard into the project. So now we need to look at how we need to integrate the power board. So when I was thinking about how I wanted to go around designing a Raspberry Pi Game Gear, I really wanted to keep the power board and the soundboard. The soundboard integration, as we've seen, is pretty simple and easy. The power board integration had the potential to be simple, but I felt I needed to complicate it. So what we could have done is I could have just connected the Game Gear power board directly up to the Raspberry Pi because it gives out 5 volts, and when I turn it on, 5 volts would go into the Raspberry Pi and it would boot up, and when I turn it off, the power's cut and it turns off. But I've been using Pis for a few years now. I built like an automated photo frame that pulled stuff down from Flickr, and I built a weather station as well. You can see the weather station online. It's at Limited Weather on Twitter, and that basically tweets out every 20 minutes the status of the weather. So this Pi is running 24/7. It's always writing to the memory card. It's always working. Now the problem there is that it will corrupt when I restart it, because it's always working, and if you pull the power out for any reason, it's writing to the card, and when I boot it up, I usually have problems. So I've had to re-image that weather station about 5 or 6 times in the 3 or 4 years it's been running. So I know that cutting power to a Raspberry Pi is a recipe for corruption. And if you look on the forums and you look on the Facebook groups of people that do this sort of thing, you do see every now and again someone will say, "Oh, my Raspberry Pi doesn't boot up anymore," and basically you've corrupted the boot partition by just powering it off. So what I wanted to do was avoid that problem. In order to do that smartly, it requires a little bit of a circuit design. So what I've come up with is a circuit that allows you to turn on the Raspberry Pi and then uses pins from the Raspberry Pi to ascertain the status of the Pi and to send a signal to shut it down cleanly. And when the Pi reports that it's been shut down cleanly, we turn it off using our soft switch. So the soft switch that I picked is the Pololu 2808. I don't recall exactly why I picked that one. There's probably others. There's probably others that are better suited to the purpose, but I didn't know at the time, and I just Googled it and I just picked one. So I picked that one. It was relatively cheap. So that is what will be supplying the power to the Raspberry Pi and our discrete logic. So the way we're going to control that switch is I've got 2 switching regulators connected to the output of the Game Gear power board. Now I could have just taken the 5 volts directly from the power board, but I don't trust that power board 100%. They do fail. So all I've done is I've hooked it up so the input voltage, which is nominally 9 volts, is flowing into the 2 5 volt switching regulators. So I have one regulator that is always energized, and I have one that is connected to the switch. So in this example, when we turn the Game Gear on, we flick the switch, dump, 5 volts flies out of the voltage regulator into our circuit. What I've got is a capacitor here that's jumping the on signal into the control logic and turning the 2808 on. Now the reason that's happening is because I didn't want to power my IC, so I'm going to have a 16 pin 7402 logic gate chip. I didn't want to have that powered from my constant current source. It would be drawing current all the time the Game Gear switched off, and for no reason, because the logic isn't needed at that point. So what capacitors act like is they are transparent to AC voltage. So the voltage will be 0 or 5. When I flick the switch, we're going to have a rising edge. And what will happen is that 5 volts will hop directly across the capacitor. And so it will be 5 volts this side and 5 volts that side. Then that will be sending a high into the control signal, and it will be energizing the 2808, and that will then be flowing power into the Pi. So this will turn on and flow power into the Pi. Once power is into the Pi and into the IC, the logic will kick in, and this gate here will be putting a 1 in this position anyway, and we no longer need our capacitor to be there. So I've got a 10 microfarad capacitor and a 200k resistor, and that's just so the voltage will jump up, and then it will stay high long enough for this gate to then kick in and maintain that high signal into the control. So that's why that is there. So that is it. That is the easy part. The Pi is turned on. There's power flowing through the 2808 into the Pi and into the IC. This logic here is now energized. There is a reinforced 1 flowing into the control logic, so the whole thing feeds back to itself. It's always on, and that's fine. So what we now need to do is we need to look at what happens when we switch off. So pin 21 of the Raspberry Pi is configured to indicate the status of the Pi. It is inverted. So pin 21 will be low when the Pi is on, or when the Pi is in the active state. When the Pi is in the shutdown low power state, it will be 3.3 volts. So the logic we're using here is a 7402 logic gate. That is TTL logic, and TTL logic has a switching level of about, at 5 volts, it's about 1.4 volts. So anything above 1.4 volts is high, anything below is low. So that works to our advantage here, that I can take in the 3.3 volt signal from the Raspberry Pi into a inverting buffer, and that will be taken as a switching level, and that's good enough. So I'm converting from 3.3 volt logic to 5 volt logic without actually having to do anything. So in normal operation, we'll have a 0 here and we'll have a 1 here. So high voltage will be flowing into the input of the NOR gate. Now a NOR gate gives out a 0 for any 1 in. So if we can see here from the truth table, 2 zeros in give me a 1 out on the NOR gate. NOR gate is the opposite of an OR gate. So an OR gate gives me 1 out for any 1 in. And there's also another gate called an exclusive OR gate, and that will only give you a 1 out if there's only 1 in. So it would, the truth table for the exclusive OR is that. So that's another type of OR gate. Yeah, but for this one, we're using NOR gates. NOR gates are pretty much the cheapest gates to build, the cheapest chips to make. NOR gates and NAND gates both are usually used by default, and you only really use AND gates or OR gates or exclusive OR gates if you don't have NOR or NAND gates to hand. So in the on state, we've got a 0 here, a 1 here, so it's feeding a 1 into here, which means there is a 0 coming out here, a 0 going into there, and again a 1 coming out onto our control, and that is reinforcing the fact the switch is on. So when I turn this switch off, click, there's no volts flowing into my regulator anymore. There's now a 0 here. That is sending a high into pin 20. Pin 20 on the Pi is waiting for a high. When it receives that, that's the shutdown signal, and it begins to initiate the shutdown process. Shutdown process, I've checked from the Pi log, takes anywhere between 8 to 12 seconds. So once this high is received, 12 seconds later the Pi is shut down and we can power it off. The problem is that this pin here, pin 21, for some reason changes state about 3 to 4 seconds into the shutdown cycle. So if we were just to feed pin 21 through a buffer directly into our logic without anything to counteract that, we would depower our Pi about 8 seconds before it's ready to be shut down. So in order to mitigate that, I've got a resistor and capacitor pair here. So what's happening is, while this is high, we're charging our capacitor. When this goes low, we just discharge our capacitor, and these two values here are picked in order to provide us enough time to find that discharge point. So in order to work out how much time that gives us, we need 0.7 RC, and that will tell us how much time we have until our voltage here reaches the halfway point between its high and its low states. So if we bring up the calculator, and we can work out how long this will give us. Yeah. So we have 24K, so that's 24,000. So 24000. Whoop, clear that. 24000. So 24,000. We're going to times that by 47 microfarads. So that's 470 times 10 to the minus 6, which looks like this. So 0.000. So this is our milli range. Then we're in our next step will be our micro range. So that'll be 470. So that's 470 microfarads. So we times those two together, and that gives us an answer of 11.28. So we times 11.28 by 0.7, and that gives us just under 8 seconds. So that number gives us 8 seconds, and 8 seconds means that after this goes low, there is 8 seconds before we're at 2.5 volts. So if you crunch the numbers, it's roughly 11 seconds before we reach the 1.4 volt switching level for TTL logic. So that means that once this goes high, this goes low, we've got about 15 seconds before this goes low. There's two zeros in here, there's a 1 here, there's a 0, there's a 1 here, there's a 0 here, 0 to the control. The control is disabled and the power switch is off. About 15 seconds. So if we look at the whole workflow again, just to get an idea of what's how of the two states. So game gets powered off, everything's turned off. We pick it up, we flick the switch, we turn it on. Volts flow into the switching regulator here, 5 volts here, 5 volts jumps across this capacitor into the control, 5 volts goes into control, the control is turned on, power is then flowing to the Pi and to the IC logic down here. The Pi is turned on, pin 21 is low, which means there's a 0 into this gate, a 1 into here. That 1 charges our big fat capacitor. Think of it as a bucket. It's filling the bucket with voltage. And that makes this input 1 as well. So we've got two 1s here, a 1 from this switch and a 1 from this logic gate. Two 1s into a NOR gate produces a 0 out. So we've got a 0 out here, a 0 into an inverter produces a 1 out. So we're reinforcing our 1 into our control and reinforcing the power here, keeping the 2808 on. So our logic, our Pi stays on, we play our games, we're having a great time. Hours, weeks, months later, we want to turn it off. So we disconnect our switch, clonk. We are now flowing a 0 into this inverter, which puts a 1 out, a 1 into pin 20 of the Pi. Tells the Pi it's time to shut down. About 3 to 5 seconds later, pin 21 of the Pi will go high to indicate that the Pi is almost in its shutdown state, but as we explained before, not quite, because this pin goes high too soon. A 1 here would be a 0 here. A 0 here will drain our bucket of voltage over the course of 11 seconds down to 1.4 volts. After 11 seconds have elapsed, we have a 0 flowing in from the switch because it's disconnected. Actually, I need to put, a 0 flowing in from the switch there, it's disconnected. A 0 here because we've used all of our resource of voltage that we stored in this capacitor. Two zeros into a NOR gate produces a 1 out, as we see here, 0, 0, 1 out. We've got a 1 here, a 1 into an inverter is a 0 here, a 0 into our control, turns off our power. So that's how it works. There will be two components continually drawing current from the power source, this one and this one. The 2808 draws 0.1 microamps. So our regulator here with no load on it is drawing a milliamp, and your typical rechargeable battery, this isn't one, but I would recommend a good rechargeable battery for this project. You're going to have 9 2700 milliamp hour batteries. I've design a circuit that does the purpose I want and I'm not killing my batteries, it's fantastic. Might want to do some testing on that really to see if it's the case. And obviously if you've got non-rechargeables, they have a lower milliamp hour rating, like somewhere in 1 to 2000. Next step is to finish building it. So I've ordered some of these components, but they have yet to turn up. On this board I've got my 2808 Pololu soft switch. I've got the big capacitors here. So the black one is this 470 down here, the big one, and the little blue one is a 10 microfarad there. I'm using electrolytics for this because they have a better storage capacity than ceramics, and also this is a through-hole board, so they're better suited for through-hole usages. In this space here will go my 16-pin IC, that's the 7402 NAND gate chip, TTL NAND gate chip. I'll go there, and on this end I'll have my two switching regulators, which are small packages that take up about 3 pins width on the board, and they'll go here and here. Then I end up with a board I need to add to my Game Gear that is about that big. Yeah, so that's the next step. Finish the board, install it in the Game Gear and test everything, and then try and fit it all in and make sure it works. So there's a saying, you see it in movies, no plan survives contact with the enemy, usually said by a general or some military hard case. It's true though. So the plans changed as I sort of worked through the circuit. I had some teething troubles, and we'll go through those. What I think I will do first is we'll test the circuit. You see there when I'm moving it around, it's kind of it's the capacitiveness of my skin is actually triggering the switch very short, in little short bursts. So it's something to be aware of. Obviously, when it's in the case, that stops being a problem. So got the Game Gear board broken out here with the with a variable power supply connected to it. I think about 12 volts it's set to, yeah. And then it goes into this board where we've got two switching regulators into a a soft switch, which is controlled by a logic chip, and then this big capacitor which deals with timing, keeps the circuit on for a bit longer because that's what we need. So if I hold this folder up actually just over the screen like that so you can see it, and then I'll turn this on. So when you turn the Game Gear power board on, power goes to the Pi and to the screen. It starts off blue because it hasn't detected the HDMI input from the Pi, and now it has. You can see in RetroPi is loading there, and that usually takes a few seconds to load up. And then you see the emulation station splash screen. All of the splash screens I think you can disable. So let's start a game. There's only one game on here. Obviously it's Chase HQ. I've got a power warning on the Game Gear. I don't know if you picked that up on the camera, but basically I don't think the wire is good enough. So when I actually wire it in, I'm going to run a thick wire to carry the 5 volts to the Pi, and that should solve that problem. So yeah, start our game. And then we play the game for a bit, and when we've had enough, as you would with a normal Game Gear, I switch the power switch off. What happens now is the Pi goes into shutdown mode, and I think you can see the text on the screen, and then a couple of seconds later this red LED will go off, and that's the power disconnected from the Pi. So what's actually happening? Well, if we again, beware, it'll flicker if I touch it too much. If we go back to the diagram, the circuit diagram that I showed you last time, there's a couple of things I had to change. So this input here is the sense input from the Pi. So when the Pi is on, this is, well, I wanted it to be 0 when it's on and 3.3 when it's off, but you can't set that, or I couldn't figure out how to set it to that mode. Like active low yes, active low no didn't work in the DT overlay config. So what I did instead was I removed this inverter, which was acting as a buffer. So that what this was doing is taking 3.3 or 0 and upping it to 5. But anyway, we removed that, feeding the 3.3 volts directly into our resistor capacitor pair here. Now I increased the value of this resistor from 24k to 36k, so by a third. And that's because my voltage is decreased by a third. So I need my circuit to sort of, and these are all ballpark figures, but I need this to drain 1/3 slower than it did before. So now what happens is when the Pi's on, current flows into here, the capacitor charges up, the voltage level on this leg rises to 3.3 volts, and there it stays until we turn the Pi off. And then what happens is slowly that voltage level decreases, and when it gets to 1.4 volts, we will then switch the control and switch the power off. So yeah, that inverter's gone. Then I had this kind of hot wire circuit, so I could send a pulse into the control and turn it on. So this was causing a weird sort of feedback loop on power off. So after I powered off, this resistor capacitor pair that I've crossed out was kind of charging and discharging and turning itself back on about 5 times before the charge finally dissipated completely and allowed the Pi to sort of stay asleep. So that was unforeseen, and I'm not really sure where it's coming from. So the easiest thing I found was to take the circuit out, and it turns out I don't need it anyway, and it works fine. The other thing was that I was going to power the IC, and that's one IC is these 4 gates down here. I was going to power it from the soft switch, but I found out when I did that, what would happen is on shutdown, when the switch turned off, the power to the IC would disconnect, and then you get weird behavior on the outputs of these gates, which would then kind of have sort of a low voltage going through the whole system all the time, and the screen would be on in a weird sort of half on, half off state, and I'm sure the Pi wasn't doing the Pi any good either. So I had to move that IC, and now the IC is powered from the constant voltage source that is always connected and always on. Other than that, there's not that many significant changes to the circuit, and what I'll do is I'll draw this up properly and link it in the description, and you'll be able to see that and use that if you want to in your build. So let's go through what happens when the circuit powers on and powers off. So what we're really interested in is the last pin on the bottom of the soft switch. So if I hit that, at an angle, you can see what I'm doing. There we go. So when we turn everything on, you can see the control jumps up to 4.9 volts. Turning it on, that causes power to flow into the Pi. So the Pi is now on, and we can see, you can just about see it's booting there. So we'll let it boot up. So now what's happened is our capacitor is charged. So if we look at one leg of our capacitor here, you can see it's just finishing its charge cycle. It's just getting up to 3.3, where it will stay around about there. So now I know that our system is fully on. So what we can do is we can now monitor the leg of the capacitor, because that's essentially what's keeping the whole system on. So I turn the game gear off. You can see it's sent the shutdown signal to game gear. That output pin 21 is now gone low, and you can see there we are. Our capacitor is drained below the switch off voltage for the TTL chip. Well, and like I said, if I touch anything, it can turn on and off. So that's what caused that. But yeah, so the capacitor drained and it turned the whole system off, and that's how it works. So it's working. It's doing exactly what I want it to do. The next stage is to integrate these bits back into the case, and I think that's probably one of the hardest bits, is finding enough room for everything to be happy inside the case. So yeah, that's the next bit. I'll struggle with that for a little bit, and then I'll get back to you and we'll see where we are. So I know this has been a long video. We're getting to the end now. mostly complete. I'm going to say this project is now 95% complete. So let's have a look at some of the things that I've done, and let's take a video actually. Here is our safe shutdown power board that I've been talking about for most of this video. It's on the flip side of this board, obviously we're looking at the bottom of it. I think what I might do is design a PCB for this actually, and then if I do use it for projects in the future, if I start making these as something that you can buy, then this will fit in much nicer in that way. And I think for most of it, this wiring scheme kind of needs to be replaced. It's a bit ad hoc as well. So next we've got the power board here. There are 3 wires coming from the power board going to the safe shutdown. There is a ground, which is the first wire here. There is a switch to 5 volts, which is turned on from the switch there, and then there is a non-switched 5 volts, which is wired to the back of the board, and that's a wire that's coming into the back of the switch. So the input to the switch always has volts on it. If you have batteries or you have a power supply connected, that's where the volts come in. The coil you see here, and there's some inductors as well. They are there to share the power between the batteries and the power supply, and then the plug here actually has a sense leg on it. So when you plug in, it knows that it's got power supply plugged in and it disconnects the batteries, and that's how all that works. But yeah, the power gets to that switch, so that's where we've hooked it to. As we talked at the beginning of the video, that's the soundboard hooked up, so it's power, ground, left and right. And the upper and lower shelves are all connected by disconnects, so these bits here can all be disconnected, and then the speaker is just unplugged as it was with the original Game Gear. What else have we got? Well, we've already covered this in previous videos. If you look at this HDMI connector here, this is a new thing that I've made to replace the old connector. This is the old connector, and that is using the KeDei jumper that came with the screen, and I extended it out, and I found it to be unreliable. Basically, like if I needed to bend it around. The HDMI connector is not designed to be soldered to, and it just failed. So throw that away. Don't want that anymore. What I did is on the old eBays, I bought a HDMI plug that is designed to be soldered to. So it's got these little cup receptacles on the front and back, and that's what we did. So an HDMI cable goes pin to pin. So I've used rainbow cable here because I got some and I thought it'd be fun to use. But on each connector, the blue wire goes to the same pin on the connector, and you just follow that scheme, and then you should be fine. That does mean that, if you can see here, the cable does need to twist over to get the wires the right way on the other side. Then this black structure here, you can see that is a 3D printed support for the Pi, and it goes into the jumper holes, the standoff holes on the Pi, and then just stops it from touching the board and just holds it in that position. Other than that, it is still free floating in the case. I haven't designed anything that captures it really and holds it still. Haven't decided if it's something I need to do or not. Yeah, all the 3D printed parts for this project, so the button holders, the switches, and then this thing will all be available on ThingiVerse, and that's linked in the description if you want to look at that. And like I said, a circuit diagram for that is also linked in the description. So that is it. That is the Game Gear Pi. So all I need to do now is put it back together and power it on, and we can see it working. Here we have our fully assembled Raspberry Pi. I'm going to say 95% finished. It still needs a couple of things doing to it. So let's turn it on and see it boot up. Like I said, that blue screen is the HDMI screen. There's nothing I can do about that without changing the firmware on the screen. I wouldn't even know where to begin. Then we can see RetroPi boot up. So what do I need to do to finish this off? Well, I think mainly is just the power LED. There's no power LED, as you can see. There's no indication that it's on. That LED I want to blink or change color when power is low, so there will be a circuit involved, and I'll have to look into how to design that. but I've kind of run out of time on this project right now. There will be a part 5 to this video, but it's not going to be right now. So if you're watching, if you're waiting with bated breath, it will be a month or two before I get to part 5, where we deal with the power LED. But that would be a really simple circuit, and there are off-the-shelf solutions out there that you can find for that kind of thing. What would I do differently? Not much. I'm pretty happy with the way it came out. Definitely wouldn't use an HDMI screen next time though. The HDMI connector is cumbersome. While the quality of the screen is great and I'm really pleased with the way it came out, using that HDMI adapter inside the case here and not, say, composite video or an SPI screen really was a massive hassle. It took 3 goes to get that connector correct. There was the first attempt, which you didn't even see, the second attempt using the jumper, and then the third attempt with the rainbow cable that's in there now. So it took a lot of work to get an HDMI, and HDMI is fiddly in this kind of form factor. So that's definitely something that I wouldn't do next time. So yeah, let's fire up some games. I wanted something to test all of the buttons. So let's look what we've got on our Super Nintendo. Oh, Street Fighter 2. This sounds nice and clear. I mean, it goes right up. Goes super loud, but you wouldn't really play it that loud, would you? So it's about there, it's probably good. So like I said, this is wired up to have, like I said in the part 1, I think maybe, or even part 2, this has a Super Nintendo number of buttons on it. So there's 6 face buttons, 1, 2, 3, 4, 5, 6. The 2 triggers up here. There's a start button obviously, and there's also a hidden select button, which is a touch button in there, which I can't remember which one it is. So what we can do is we can start a game. What was the version? It always went to Dal Sim it drove me crazy. It's so boring. So you can see I've got hard punch, hard kick on my shoulder buttons. Then medium kick, soft kick, medium punch, and little jab. And I'm dead. So yeah, I know all the buttons are working because we've tested that in previous video. You saw the Teensy being tested in Windows. But yeah, so that is pretty much it for the Raspberry Pi. If you need to come out, is start and select. So the 2 touch buttons are actually what bring you back to the Pi menu, and then you can come back to the top menu like that. Yeah, so really pleased with the way this build came out. I'm pretty sure this will be something that you will be able to buy from 16-Bit Bench if I'm not selling them already. Contact me to ask. I'll also make the kit available, kit of parts on ThingiVerse. So that is the buttons, the shoulder triggers, the little sort of harness inside for the Raspberry Pi, and then the button holders that are under the front here. All of that stuff will be for free on Thingiverse. The PCB, if I have that designed, that will be something chargeable from me, and that will be, you know, a few pounds, and a little bit more expensive if you want the parts on it. But yeah, so I had a great time designing this. It was a lot of fun, and I'm glad you could come with me and you saw the ups and downs and the way we had to go back. I know this has been a really long video, and I'm sorry for that. I just wanted to get everything into the last part. Well, there will be another part. There will be a part 5, but we're not quite there yet. So I want to thank everyone for watching. If you found it useful, please like and subscribe to the video. Really helpful to me getting more visibility on YouTube and getting more people seeing my videos. That would be really good. Find us on Facebook, Twitter and Instagram. It's 16-Bit Bench. Yeah, and thanks for coming by, and we'll see you next time.
Now to sport with Meredith Sheehan.